Hi, and welcome back. We are going to talk about 5.2 today, which is all about polynomials. So this will be our first introduction to polynomials. We'll continue to work with these pretty much from here on out, different variations over the course or over the course of the course, if you were to think of it that way. All right, so let's talk about polynomials. The first and foremost thing is on your notes, you'll notice that there are a couple definitions. I'm going to rely on you to use these definitions right here in the notes, as I am not going to write them up here on the board. You already have them written. That being said, when you're looking at polynomials, there are a couple key terms. The first one is a coefficient value, and this is simply the numerical value that you see in front of a variable. Very simple, very straightforward. The next term, and the next three terms really, are talking about different types of polynomials. So monomial, you're talking about a single term. Binomial, you're talking about two terms and you're combining those two terms through either addition or subtraction. If you're looking at a trinomial, guess what? You're looking at three terms, tri being the key word or key component of that word. So you're looking at three terms. You are combining those three terms through addition and subtraction. Okay, as you start to get more than three terms, that's where you start getting the term polynomial. Hence, we are talking about polynomials. We are talking about all variations thereof, be it one term or be it, 20 terms, whatever it happens to be. What does this actually look like for us? Let's go over a couple examples. If I were to look at a very simple example, something like 3x, just as a quick idea. This is not an example per se, I'm just helping to flesh out the idea. When I'm looking at this particular item, this is a single term, and that is what we call a monomial. In this structure, I see a numerical value. This is our coefficient. And then I see another piece. This is our variable. Now, whenever you're looking at a term is always combined with multiplication or division. Now, as I'm looking at this particular term, I have just the one, it's 3x. That is a monomial term. If I were to say combine this with something else, now I'm looking at two terms. I have this term and this term. Now notice this term has an x variable to it, meaning I have a coefficient and a variable. But this term has no variable. Technically, it does have a variable if I were to think of it as like x to the 0 power. If you recall from our exponents lecture, anything raised to the 0 power is 1. So this is really like 7 times 1. And so you could imply that there is a variable there. However, if you just see a number by itself like so, that is what we call a constant value. So you have a term and a constant if you were to think of it that way. If I were to introduce something else, such as this, I'm now looking at three different terms. And so I have 4x squared is one term, I have 3x is another term, and I have 7 is a constant term or a constant value. Now, looking at each of these components, you might notice that there's something a little bit different about each one. This has a power of 2. This has a power of 1. This has a power of 0, meaning it's constant. There is no variable there that we see within the problem. As I'm looking at each one of those individual terms, I can then explain the degree of those terms. So notice how I said the degree, or as before, this has a power of 2, power of 1, power of 0. My degree value is talking about the sum of the exponents within each term. And I'm only looking at the variables. So this has a degree of 2 for this first term. This has a degree of 1 for this second or middle term. This has a degree of 0 because I do not have a variable. And so as I'm looking at these individual degrees for each individual term, I can then say, well, if I look at all of them together for the entire problem, I can get the degree of the polynomial. And the degree of the polynomial will be the greatest of the degrees of the individual term. So the degree of the polynomial in this situation is 2. And that is because I have my largest sum of exponent values as 2. Now, you might be thinking, okay, that's a little confusing, and why do I need to know it? If you were to think back when we talked about linear equations, just to give you an idea, was something of y equals mx plus b format. And your only variables here would be y and x. And of particular concern is really the x value. So I'm going to actually change this so that it's function notation to bring that term back for us. And that function notation is really just showing us that we have the one input variable. Now, what is the exponent on this variable? 1. And if you think about what a line looks like, a line has no curvature. So as I start to increase my degree values, so this is a second degree polynomial, as I can see right here, a second degree polynomial curves. It's like a U shape, it's a parabola is what we call it. As I start to increase, let's say I have a degree of 3, just to give you an idea here. A degree of 3 starts to do this. I start to curve even more. If I were to have a degree of 4 gives me even more curvature. And so what happens with the idea of degrees and why they are important is because as you increase the number in your degrees, the degree value of the polynomial, you increase its curvature graphically. Now, why is that important? Well, if I'm creating something structurally or I'm manufacturing a product and I have something more than just straight lines connecting this product, I need curves. Those curves are actually calculated as formulas. They come with degrees as a polynomial. Okay, that being said, that's a little bit of background knowledge to why these are important. Let's jump into some examples. So we're going to look at just degrees of terms first before we go into degrees of polynomials in greater detail. So if I look at my first example in the degree of a term section, that's this little definition section right down here in your notes. My first example is 2xy. Remember, if I'm looking at the degrees of the term, I'm looking at the variables only, and I'm adding up their exponents. So in this case, I have an exponent of 1 on the x, an exponent of 1 on the y. So my degree in this example is 1 plus 1, or 2. If I have 14x, again, looking at only the variable, I have x, it's technically raised to a 1, which means my degree value is 1. If I were to look at the value of just 3, this is a constant. There are no variables here, but if you need to see it, it's technically x to the 0. And that means I have a degree of 0. And if I have a term that has multiple variables and exponents with those variables, such as this, I have 15x squared y to the third z. I'm looking at each of these variables, combining their exponents. So I have 2 plus 3 plus 1. I have a degree value of 6. So I'm looking strictly at the variable exponents, and I am summing the exponents within a single term. Okay, very good. Now let's go into our degree of a polynomial. So I'm going to get some board space back up here. If I were to look at 7x to the fifth minus 6x to the third, the question that I would get is find the degree of the following polynomials, or find the degree of the polynomial. To find the degree of the polynomial, just one more time, as we already mentioned this, I have to look at the individual degrees of each term within that polynomial. So in this case, it's very simple because I only have one variable in each of these two terms. I have a degree here of 5. I have a degree here of 3. The degree of my polynomial is the greatest of these, which is 5. What if I had just -8 as another example? Just -8, that's a constant value. We know that the degree of a constant value is 0. Therefore, the degree of this polynomial is 0. What if I had, getting plenty of space here, p plus 3p to the fourth? My degree of this first term is 1. My degree of this second term is 4. The degree of the polynomial is 4. It's pretty straightforward. And if I had something like m to the 9th minus 4m to the 10th plus 3m squared. Compare your degrees. I have 9, 10, and 2. The degree of the polynomial is 10. Again, the degree of the polynomial will indicate curvature within its graph, and that means a 10th degree polynomial has a lot of curvature to it. Okay, so let's go a little bit further with this. Now, I did mention function notation a few moments ago with an example. I want to just kind of go back over function notation and how that really works, because we are jumping into an area of math that will start to utilize function notation more. So this next example is q of x is equal to 8x squared minus 4. And it says find q to the negative second, find q when x is the -2, or q of -2, and find q of 0. So find q of -2 and q of 0. Good. I found them. There they are. Just kidding. All right, what we're going to do is we are going to plug in our values. So q of -2, we simply plug in. Again, with function notation, you really want to use those parentheses. That way you don't lose your sign. So input wherever you see an x, because that was our input variable. I have -2, putting that in. And then simplify from here. So I have -2 squared, which is 4. So that's 8 times 4 minus 4. 8 times 4 is 32 minus 4. And 32 minus 4 is 28. So q at -2 is 28. Remember, this can also be translated into a coordinate value if you were to graph. Just to give you an idea, this would be a -2, 28 as a coordinate value if you were to graph this polynomial. All right, let's try one more, that q of 0. So at q of 0, plug in. 0 squared is 0. 8 times 0 is 0. Minus 4 is -4. So q at 0 is -4. That one was a very easy one. Again, if you were looking for a coordinate value, that is 0, -4. Okay. Now, This is just a little quick refresher on function notation. Again, it is something that will pop up more frequently now that you have been exposed, multiple times especially. It's not too bad. But now we're going to kind of shift gears into working with some polynomials. Now, working with polynomials, you can do things like adding, subtracting, multiplying, dividing, etc. We're going to start with the basics. We're going to go with adding and subtracting polynomials. So if I were to look at an example, 3x plus 2 minus 4x plus 7, and I told you to simplify, or I told you to combine like terms, or solve, which you wouldn't really see solve on this because it's not an equation. But you may see something like simplify, and that's the only instruction they give you. What you're looking at here is you would have to combine your like terms. And so it helps to identify where those like terms are and what those like terms are. So in this example, it's pretty easy. I can see that I have a 3x and I have a negative 4x. This is a minus 4x, so that sign carries with it. That is an x, just to be very clear. And then I have a positive 2 and a positive 7. And notice my technique for identifying like terms. I used one underline to identify one like term. I used a double underline to identify a different like term pair. Okay, now that being said, we're going to go ahead and combine our like terms. So 3x minus 4x is a negative x. 2 plus 7 is 9. And that is it. So technically what you're doing here is you actually subtracted one polynomial from another polynomial. You added your polynomials together, excuse me. You technically combine those polynomials together. Okay, now, that being said, let's try one more, and then we will get into a further set of examples, and this might help if I write correctly. So I have 10y minus 12y minus y squared. There we go. Identify your like terms. I have 10y, I have a negative 12y. This y squared has a different exponent. It has a different degree value. Therefore, it is not like just y. So this term is all on its own. It is what it is. Sad, tears, I know. 10 minus 12, negative 2y minus y squared. That's it. That's all there is to this one. Okay. There we are. I want to make sure I'm on the right spot. So we are going to use the next few problems as examples of adding and subtracting our polynomials. So I'm just going to go off over here and write them out. So I have my first polynomial that I'm adding with a second polynomial. That's why we are grouping with parentheses here, just like we did in our other example. And we are going to look at what we've got. Now, there's something very, very important to note whenever you're working with polynomials, and that is if you're identifying one polynomial and another polynomial, typically with those parentheses, you want to make sure that you don't have any sign changes. What do I mean? These signs in the first polynomial would only be changed if you had something out here, like a negative. This polynomial would only have its signs changed likewise if this sign were a negative. But I don't see a negative out here. This is addition, so it's not a negative, which means my polynomials can easily be combined with no sign changes. We'll see an example in a few moments where you do have sign changes though. Don't worry. That being said, let's identify our like terms. Do I have a w cubed anywhere else? No. I'm going to bring that term down. So I have a negative 8w cubed. Do I see a w squared anywhere else? Yes, I have an 11w squared and I have a negative 10w squared. Combined, that is a positive w squared. Lastly, do I see any constant values anywhere else? Yes, I have a negative 12 and a positive 3 combined. That is a negative 9. At this point, always ask yourself, is there anything else that you need to do? I have a w cubed, I have a w squared, those are not like terms, and I have a constant value. There are no like terms here. This would then be your solution. Okay, not too bad, especially for that first example, really going into several terms combining together. Let's try another one. Let's try a subtraction so you can see that sign change we spoke about. So this next one is 5a to the fourth minus 6a squared plus 9a. That is one polynomial. Minus another polynomial of a cubed minus 19a minus 1. Now, just to eliminate confusion, I am going to erase this other problem so that we are only looking at the one problem on our board. Now, do I see sign changes? That's the first thing I kind of want to ask myself whenever I'm approaching these problems. The answer is no sign change here, but this is negative, which means yes, I do have sign changes here. Let's get the sign change out of the way first. It's super, super easy. And what I'm going to do is I'm going to take this and simply, if you will, distribute the negative to each term inside. Here's what happens. The first polynomial doesn't change, so I'll bring it down in a minute. The second polynomial, that negative then distributes here. That is a negative a cubed. Negative and negative is a positive 19a. Negative and negative makes that a positive 1. My sign changes are now done for this second polynomial. The first polynomial, because there were no sign changes, I'm just going to bring it down, but I'm going to drop my parentheses. So I have 5a to the fourth minus 6a squared plus 9a. I'm subtracting a cubed, adding 19a, and adding 1. Notice that there are no parentheses now, and everything is more cohesive. So once you get the sign change out of the way, you can drop those parentheses. That's very easy to do. Now, identify your like terms. Do I have any a to the fourths anywhere else? No. So bring it down. Do I have a squared anywhere else? No. Bring it down. Do I have a anywhere else? Just a? Yes. Right there. And so I have 9a, 19a, that is 28a. Do I have a cubed anywhere else? No. So that's a minus a cubed, and then plus 1. Now, there's one small little addition that we want to put into this whole set of rules that you're working with in polynomials. And that is the concept of descending order. So there's nothing else to combine in this problem. However, there is one more thing that you can do. Notice I have my degree of 4, a degree of 2, a degree of 1, a degree of 3, and my constant value. So let's put this in descending order in terms of degree. This means I would have 5a to the fourth minus a to the third minus 6a squared, just keeping my signs together with my terms, plus 28a plus 1. And now, as I look at my degrees, I have 4, 3, 2, 1, constant. You thought I was going to say blast off, I know, but that's constant. Okay. And that's it. Nothing can be combined. You're in descending order. That is as simple as that gets. All right, let's try another problem. And I can put it right here. I got plenty of space. So this next one, also a little bit of a doozy, but it's fun. Yep, plenty of space. Perfect. Okay, so at this point, what I need to look at are where everything is. Do I have sign changes? Do I need to combine my terms, identify my like terms rather? So that's what we're going to do. Do I have a sign change in this first polynomial? No, it's going to come down just as is. Let's look at that in a moment. Do I have any sign changes here? Yes. This is a minus this polynomial, so let's go ahead and do that sign change. That is a negative 2m minus 7n minus 4, nm squared. M comes before n in the alphabet. Let's rearrange that. M squared n. So I just rearranged those two variables because I want them in alphabetical order. Very important. You'll see why in a moment. I got my sign changes out of the way. Great. Now, there were no sign changes here. Let's just bring it down, drop those parentheses. Minus 4m squared n plus 3n minus 6m. Now, let's look at what we've got. Let's see what kind of components are like terms. Do I have anything with an m squared n in the problem? M squared n has to be identical to this. Yes, m squared n. Now, if you would have left it as nm squared, as it was before, as it was originally, that is still okay because remember, you can multiply in any order. And so nm squared and m squared n are exactly the same. It just helps to see it alphabetically. So whenever you see this rearrangement that you can make, I would suggest making that rearrangement. That way you have it alphanumerically. Okay, that being said, yes, these are like terms. Let's combine them. So that's negative 8 m squared n. Do I have any just n's around? Yes, right here. 3n, negative 7n is a negative 4n. Do I have any m's just by themselves? Absolutely. I'm going to use a squiggly line here. So that is a negative 8m. And that is it. There's nothing else to do in that problem. All right. Let's try another problem. This will be our last one for this section. Now, I do have to warn you, with polynomials, it helps to write every step, which means sometimes you have a lot of writing to go, and that is okay. I am going to erase this problem because this is a little bit of a longer problem to write out, and I want to make sure I have plenty of board space to work with. So I have my first polynomial up here. I'm adding a second polynomial. And I'm subtracting a third polynomial. So you want to make sure you have everything written exactly as it is. Always double check your writing. You'll see sometimes I might have written something backwards. I always go back and double check it, and if I have to fix it, I will. So good habit to get into. Make sure you write something and you double check it. Now, let's tackle this the same exact way. I'm looking at my three polynomials. I can see my three sets of parentheses. My polynomials are very clear. Do I have any sign changes? No, no, because this is positive. Yes, because this is negative. These signs will change. Let's take care of that first. So I have negative 9x squared y minus 5xy. Those signs are now changed. None of the other polynomials had sign changes, so I'm going to drop the parentheses and bring those terms down. So I'm just going to bring them down, drop those parentheses, and that was supposed to be in perfect line, but you get where I'm going. These are in the same line. Okay. Now, There's a lot of working components here. We got several terms. Take your time as you go through and identify your like terms. I'm looking for x squared y first. So x squared y. No, 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 yes. So I have an x squared y. 2 and negative 9 is going to be a negative 7 x squared y. Notice I solve these as I go. Just xy. No, yes, and yes. Now, 3 different pieces, that's okay. 2 plus 6 is 8. Minus 5 is positive 3xy. Now, because you're working with a lot of different components, it might be easier, just as a strategy, to cross them out when you've finished working with them. This is especially true in problems where you have a lot of terms. So I've already used those terms up. That's how I've gotten to where I am so far. I now know I just need to look at the comparison of these two terms. So I have an xy squared. This is also an xy squared. I can combine those. Negative 4, positive 9 is a positive 5xy squared. Now, I've crossed those out. Do I have anything else? No. So there is my solution. The key here, and the reason I'm kind of exaggerating my motions a little bit, is because I want you to see the process on how I'm solving these problems. It's very important to go through step by step and see what exactly is changing, what can be combined, and once you've combined it, kind of cross it off your list. See what else you have left. That way you don't lose any terms, you don't lose any signs. Okay, guys, that is it for section 5.2. I will be continuing into section 5.3 in just a few moments.